differentiability. So basically, functions can be differentiable, but they can also be like basically not differentiable at a point or potentially like on a line or something like that, depending on what it is. We can have corners, cusps, vertical tangents, or just like a discontinuity. Probably the most common ones are going to be like corners and cusps that we deal with overall, but we'll see a little bit of the different types. So jumping in here, the first ones, problems 1 through 4, compare the right hand and left hand derivatives to show that the function is not differentiable at the point P. Find all points where the function is not differentiable. So if you notice in the book, there are basically, it's not one like function that they're looking at. It's like 2 separate functions, or in some cases it could be like 3 or 4 depending on where we are. But if you look at number 2, we've got a y equals 2 as an equation, and then the other line is y equals 2x. So we've got y equals 2 and y equals 2x. So what I'm basically doing is I want to take the derivative of both of these things and see if they're equal. Essentially, if they're not, then it's not differentiable at a point. Like we want, because the left and the right hand limits, quote unquote, or derivatives should be the same value. So the derivative of a constant is 0. So this one is 0. Derivative of this, it's got the exponent of 1, so multiply it. So y equals, or y prime equals 2, and the exponent or the variable goes away. So these are not the same. So these are differentiable everywhere except for at the point where those two things come together. So we would say differentiable, and I usually abbreviate it because writing that word out over and over again gets a little long. Differentiable everywhere except at x equals 1. And essentially I can also see that to an extent because it has that would be technically like a corner there. But sometimes they can be a little like misleading. So I like to show like the actual reasons behind them. So this is on the left hand side, y equals x, and on the right hand side it's y equals 1 over x. And then obviously we've got the point there that we're looking at. So I want to take the derivative of it first. So do you know what the derivative of the first one is?
1.
Yep. On this one over here, the one on the right hand side, I would probably suggest you rewrite this with x being like on the top of the fraction. So rewrite this as x to the negative 1 because, well, we can take the derivative of something in the denominator. However, you don't have all the rules to know how to do that yet. So I would rewrite it this way, makes it nice and easy. Then we take this negative 1 and we put it in front. So that would be negative x. Then we subtract 1 from this, so it would be to the negative 2, which obviously we could then rewrite if we were so inclined as negative 1 over x squared would be what the derivative of that would end up actually looking like.
Why is it x to the negative 2?
So we subtract 1 from here. So when it's negative numbers, it's going to just keep getting smaller.
Okay.
So it's kind of weird because obviously, like, if you had just, like, x, then it becomes, like, just 1 and it goes away because it would be, like, x to the 0. But if you have just a constant, it's gone. So the only way that you can really ever get this situation is if you start here.
I got
like to end up with negatives, or if you just like they start you with a random function that has negative exponents, essentially. So obviously this one didn't end up just giving us a number. So I'm going to look at, well, at the point that they're asking me to evaluate, which is 1, 1. So if I put in 1 for x, then I end up with, you can write it like that, negative 1 over 1, which ends up just being negative 1. Well, again, these are not the same value at 1. We would be plugging in over here if this wasn't coming out to a constant. These are just coming out to constant values, so we haven't had to do that yet. So that means that this is differentiable everywhere except at, again, x equals 1 in this particular case. This problem to me looks a lot like a cusp. The cusps kind of look like when people draw those like birds on their like artwork. That's what I kind of think of when I'm thinking of a cusp, but I mean they can obviously look a little different than that, but all right. 5 through 10 also have pictures with them. So the graph of a function over a closed interval D is given. At what domain points does the function appear to be differentiable, continuous but not differentiable, and then neither continuous nor differentiable? And it's possible for like multiple of these things to be like that there aren't any, or there could be something in all of them potentially. So we'll start at 6. So 6, we've got a graph that kind of sort of looks like a cosine or a sine function potentially, but most likely it's not just because of what it looks like, but kind of has that vibe going for it. And so basically looking at the graph, I'm looking at where is it differentiable? Well, that function keeps going. I don't see any areas where I have a corner, a cusp, a vertical tangent, or just like a discontinuity. A discontinuity would be like when we have that, if you remember from the basic functions last year, like the integer of x, like a piecewise function, that's a lot of times going to be an automatic discontinuity, which means that the derivatives don't exist. So this one to me, I would say is differentiable everywhere, but I would want to specify on its domain. So I would say for part A, where is it differentiable? On all points in the closed interval -2 to 3. Because there's nowhere where it's doing anything like weird, basically. Part B, continuous but not differentiable. So that could be where the function, it keeps going, however, it has one of those like corners, cusps, or something like that. We don't have that situation in this one, so this one would be none for this part. And then part C, neither continuous nor differentiable. Well, there's nowhere that that's happening because we've said it's differentiable everywhere, and it's obviously continuous along the whole thing. So there's nowhere that that's happening in this one either. 8 will be a little more involved, so we can look at that one. All right, so 8, we've got, again, we've got the same domain, -2 to 3. The left kind of part over there kind of gives me a vibe of an absolute value function. And then it kind of looks like an upside down parabola, and then a random point thrown in there on the right-hand side. So I want to know, where is it differentiable? So anytime you have something where it's like fully changing directions like an absolute value, where it's producing a corner, that's going to be not differentiable there. Any place where it like jumps, so it goes from like something like not filled in to something filled in a different spot or whatever, that would be a problem. So at 0, it looks like there's an issue. And then again, where there's like a hole and then something else, obviously not differentiable there either. Wherever that's happening, as that would be like a discontinuity in it. So this one's a little bit weird the way that we'll write this one, but basically it's differentiable at all points in the closed interval -2 to 3, except at x equals, what's that, -1, 0, and 2. Now, there's not really a good way to, like, write this. I mean, the book writes them this way. It's probably the best way to write it, because otherwise you'd have a bunch of little tiny intervals that you'd be, like, unioning together. Continuous, but not differentiable. So basically, where does the function actually, like, keep going? And that would be, to me, looks like at -1 that's happening, because there's no, like, hole or whatever. It's just basically the graph's going and then it just turns around and keeps, going the other way. There's no, like, gaps in the function there. So the only place to me that it appears that it's continuous and not differentiable is at -1. So be at x equals -1. And then for part C, neither continuous nor differentiable. Well, any place where there's, like, the jump discontinuity, which would be what's happening at x equals 0, or we have the removable discontinuity where there's, like, a hole, that's obviously, those aren't differentiable, and they're also not continuous. So at x equals 0 and x equals 2, we would have issues there. Or that would be part C. So basically, your part B and part C will pretty much be whatever values caused a problem in part A, where it's not differentiable. Most of the time, that's going to be basically all of your answers to B and C. So once you've used them all, essentially, you're done. So let's see. Let's go ahead and look at 10 also. So 10, we've got straight line going up into basically a parabola, and then a straight line coming down out of that. So any idea for part A, where is this function differentiable, or where is it not differentiable?
-2 and 2.
Yep. So part A, all points in the domain is -3 to 3, except x equals -2 and x equals 2. Or you can put commas in there, whatever. So then part B, continuous but not differentiable. So basically at these 2 points, are they continuous or not? Because if they're not, then it would go in part C.
Yeah, they are continuous.
Yep, they are continuous. So they'll go in part B. It's basically continuous but not differentiable at x equals -2 and x equals 2. And then part C would just be none, because there's no other values that we're dealing with on this domain. Okay. Next problems here. There's a couple different ways you can kind of do this. If you kind of roughly know what the stuff in 11 through 16 would look like, you probably could do this just kind of on your own. If you're not really sure what they look like, then you would have to essentially graph them, which obviously you can either do by plotting points or by, just using your calculator. I would probably just use your calculator for these, because really all you're trying to do is see what type of, where it fails to be differentiable, and we'll just state the name of the type. So let me see, where did I stick my calculator? Okay, so we'll do 12, 14, and 16. So 12, we've got y equals x to the 4/5, and we want to see what this looks like. And some of them, depending on how they are, we may need to like adjust our window so that we can see everything. But let's see, y equals x raised to the 4/5. Zoom 6. So at initial glance, what does this kind of look like?
An absolute value.
Yeah, kind of looks like an absolute value function, which would mean it would have what kind of differentiability?
At 0.
Yeah. Is it a corner, cusp, vertical tangent, or just continuity?
Corner.
So it looks like a corner, but that's what I was saying. If we zoom it in here and we box this, we should see that these actually aren't straight lines here. These are actually slightly curved. So if you zoom box it, and I wouldn't just know that off the top of my head if I hadn't done this one before, but I would always kind of like zoom it in a little bit if it's something like this where you can't tell for sure, because when we do it, I can kind of see that it's arcing a little bit. I can see that they're not just straight lines. So basically, if they're arcing at all, it's going to be like your bird situation where it's actually a cusp on these ones. So if I were to ask you this on like a quiz or a test, I would suggest that you draw like kind of a rough sketch of what it looks like when you write it, because if you put corner, I probably would maybe only take like 1 point off if you like, because obviously it does kind of look like a corner, but this one does happen to be a cusp just because of the curving of the lines. That's obviously kind of hard to see, but it is on there. 14. Y equals 3 minus the cube root of x. So 3 minus, I don't know if you remember how to do a cube root, but under math, and then arrow down, option 4 is a cube root, and then there's the nth root is the one below that. And then if you boxed, I would do zoom standard again so that you can see what's happening. So obviously this graph looks very different than the other ones that we've had so far. This one looks kind of similar to the example I did in the notes, but for like the cube root of x. Obviously this one's a cube root of x that's reflected and shifted over, essentially. So basically, because this is going out like that to essentially infinity and negative infinity, this one has to have a vertical tangent. And then 16, y equals the cube root of the absolute value of x. And absolute value bars are also under math, under number, so that you can put that in there like that. So this one is also a cusp. It kind of like curves in there. So even though we have the absolute value, since it's in the cube root, it's going to kind of make it like more curvy looking. So it ends up being more of a cusp than anything on this one. Almost anytime you have a piecewise function, it's just going to be a discontinuity. Because, again, if you take the derivative of, like, both pieces, you'll see it. Now, the one that's in here, like number 11, you aren't going to be able to necessarily see this. You wouldn't be able to find it mathematically by hand yet. You'd have to basically try to look at the graph or see, like, roughly what a graph looks like. You'd have to essentially see what an inverse tangent function looks like and know that it's everywhere but 0, and then at 0 the value's 1, and it's essentially going to show you that it's, like, jumping up. So it's going to have to be a discontinuity. But most anytime you have a piecewise function, it's going to be that way. Unless it's, something like what we had in 1 through 4. Obviously, those weren't discontinuities, but those were just two totally different functions. But, anyways, any questions on that?
For 14, there was like a jump, like a break in the middle. Is it still a vertical tangent?
I did not see that, so let me look. Trying to see. There shouldn't be any values that are causing an issue, so I'm wondering if it's just coming straight down over the x-axis. Let me try to zoom it in again. I see what you're saying. When it's like graphing it, it does kind of look like it is like jumping down a little bit.
Yeah, and when I zoom in, there's like a spot where it, like, there's nothing there.
Let's trace the graph. So there shouldn't be any values that are causing an issue on that.
Wouldn't 27, when x is 27, it would be y 0?
Yeah, but that would be at when x is 27, so that would be like way farther up in the graph. When x is 0, though, should be at 3. Which it's close, it's just not showing me exactly. Let me see, second trace value, when x equals 0, y equals 3. The slope of the secant lines approach either. I mean, it should still be a vertical tangent, but that is weird that it's like a jump. That's why I'm like, I don't know if it's just, if it's looking like that because it's coming so close over top of the x-axis. But I mean, when you trace it, it does clearly jump. So I'm not sure. But it's supposed to be, I mean, it is supposed to be a vertical tangent.
Okay.
Because I was trying to figure out, I was like, because there's no values that make a cube root not work. And a cube root is the typical one where you would see a vertical tangent. It's just shifted. In this case, this one shifted up 3, which could also have something to do with why it looks funny. I'm not 100% sure. Never paid that close attention to the fact that there was a jump in that one before, or what it looks like a jump. Don't know. To think about. got that. Okay. Oh gosh, I hate these ones. Okay. Find the numerical derivative of the given function at the indicated point. Use h is equal to 0.001. Is the function differentiable at the indicated point? So, if you remember, we had the other day, we had the equation like f of a plus h minus f of, well, basically a minus h, or it might be in your notes for this section, over, what is it, 0.002, I think. Find it. Oh, well, 2 times whatever h is. So in this case, it'll be 0.002. But basically, we're going to be using this formula, but they told us it's for h is 0.001. So h is 0.001. F of x is equal to 4x minus x squared, and x is equal to 3. So, we're basically just plugging this in, or this a plus 0.001 in for our x values, but in this case my a is 3. So this is really a over here that's getting plugged in. So we'll have essentially this formula is going to become f of a plus 0.001 minus f of a minus 0.001 over 2 times 0.001, so 0.002 is what we'll be doing, but we'll be plugging in 3 for a. So I will have over here 4 times 3 plus 0.001. If you want to go ahead and write 3.001, obviously that's fine too. Minus 3 plus 0.001 squared minus, and then I would probably do brackets just so you don't get it mixed up. That's just the first part. So then now I'm doing the a minus 0.001. So 4 times 3 minus 0.001 minus 3 minus 0.001 squared, and then all over 0.002. And basically, at this point, I would probably grab my calculator and type this in, because it's going to get a little bit crazy with all the stuff. So, and I would, well, it doesn't really matter if you do it as a fraction, but I like to type things in as a fraction. 4 times 3.001 minus 3.001 squared minus parentheses, or, oh. Oops. My 2 didn't click. It was like, you can't divide by 0, and I was like, I didn't divide by 0. Apparently I didn't hit the 2. So all of that, when you work it all out, actually comes out to be the nice number of -2. So they ask us, is this function differentiable at the indicated point? Well, it ends up being a number, so yes. Basically, unless it comes out to be 0, it is differentiable. So if we do like 24, f of x is equal to the absolute value of x minus 3, and we're doing it at x equals 3. I end up having here the absolute value of, I'm still doing a plus h, I'm just going to write it as 3.001 minus 3, and then minus over here another absolute value, 3 minus 0.001, so 2.999 minus 3, and then all over 0.002. Well, when I do this, essentially in both situations, I'm getting 0.001. So it'll be 0.001 minus 0.001 over 0.002. Well, obviously that causes a problem because that's going to give me a 0 on top. Or it doesn't really cause a problem, but it gives me 0. So this one is not differentiable because it equals 0. So, but that's pretty much all for this section. There's not really anything else that's like super critical in this section. Any questions? So problems here, 1, 5, 7, 11, 13, 17, and 23.